So this is where we left off last time on the mean kinetic energy equation. And I'm going to bring my notes over here. Excuse me. Small error on my part. What I want to say. This is, of course, a scalar product of uj. If we take the scalar product of uj and the mean momentum equation, which was on equation 2.50. And you can see that's what I'm doing right here. Here's equation 2.50 repeated for you. And there's u tilde j. And as you remember, that would be what? The mass average. And I do that again in the second equation, but with I, and I substitute I and j. And then what am I going to do? I'm going to add these equations. Add them. And then what do I get? I get a very useful stress equation. And you'll remember when we were doing the introductory module, we weren't doing the compressibility flows with Favre averaging, we were doing incompressible. And so this is the equivalent Favre averaged Reynolds-Stress type equation for mean kinetic energy. And we often formulate our models in terms of turbulent kinetic energy. So if we set I equals j, then 257 becomes 258. And now you'll look at the term on the left-hand side. We have ui, which we would sum from 1 to 3. It's like the trace of that Reynolds stress, if you will, and we're getting that mean kinetic energy. The left-hand side you can write as a material derivative. Which is nice right there, and there's expanding it out. So there's your material derivative written a slightly different way. So this is the kinetic energy equation of the mean motion, and there's multiple terms. This is, of course, the first term, which is left-hand side, and the other terms. And they can be kind of thought of in terms of physics. And so we'll say that this term, the first one, is a rate of change of kinetic energy of the mean motion. Oh, I should write kinetic energy, right? So it's a kinetic energy equation. Second term, 259, would be the flow work done by the mean pressure. Acting on a control volume to produce, of course, kinetic energy in the mean motion. So anything with pressure gradients and u tilde would do that. This term here, 262, it's obviously acting on viscosity, so it's an action of viscosity. Which takes form of dissipation. You probably notice that my page numbers are a little bit different than yours, but the equation numbers should be the same. So I apologize for that, but my LaTeX typesetting packages with and without the student notes is mismatched, and I can't figure it out without using slides, so sorry about that. Anyway, there's the last term of 259, and that can be expanded out like this into two parts. And you'll see the first term on the right-hand side, which is this one, it will represent the transport of mean kinetic energy by turbulent fluctuations. And some people might call this the gain from the energy flux, or the divergence of the energy flux transmitted by the work of the mean flow against the Reynolds stresses. What a mouthful. The second term is nothing but it's a loss to turbulence of the right-hand side in terms of turbulent energy. So this whole equation is a balanced equation, conservation equation. It's general, and we didn't make any assumptions whatsoever on what kind of flow it can be applied to. That being said, it's, for kinetic energy, if we just look at the Reynolds-Stress transport, and later in the class we'll look at stress transport turbulence closures, we can try and also form a Reynolds-Stress transport equation. So these equations for the velocity fluctuation components, that's what we call Reynolds-Stress transport equations. And just like in the previous section, what did we do? We said, hey AJ, we said we'll take the moments and atoms. So once again, we take our equation from 2.2. So you can see this is a, of course, momentum equation, right? Before averaging. We take the moment with uj, and then we set I equals j and ui here. Take the moment again, and we'll add them just again to try and create more equations for closure and tracking Reynolds stress transport. And this is, of course, what we get from summation of these two equations. And you'll see that this equation is a lot like equation 264 in itself. And here I made a typesetting error and actually wrote 266 twice, so you can just cross this out like I did in red. So if we use equation 220, which is u equals u tilde plus u prime, so remember that's the Favre average plus a fluctuating mass average, and this equation 266 were the moments of the momentum equation, we'll get this giant equation, which has a lot of extra unknowns in it and not much we can do. And I did make I was looking at it the other day, and I think in the next equation you'll see I made a few errors in where I put the bars. But what do we do with these? We always average them. So we'll take the average of the whole equation, and those averages reduce to term by term. And that's what you'll see in equation 269. And 269, it looks like I need a bar here, and I need a bar here, and I need a bar here. And that's where I missed in my LaTeX typesetting 3 bars. So that's the operation. Now, if we go back to equation 257, and this was the mean kinetic energy equation, which we just derived. We subtract 257 from this particular equation and do some rearrangement, then we'll find one equation for the components of the Reynolds stresses, the mass-weighted Reynolds stresses, which are right here, which we showed in the beginning of this chapter 2. So that's what this equation 270 is, which is important. So this is one equation which is tracking Reynolds stresses, just like we developed for incompressible flow. So this is a more general form for compressible flows. So how many unknowns do we have? Well, this is symmetric, so this is tracking 6 unknowns, which is a lot, right? So if we do the I equals 1 to 3, j equals 1 to 3, and it's symmetric, which is good. And this is the material derivative definition of 270. So this is a very complicated flow, and someone a lot smarter than me made a quote about it, which I'll just read for the class. And it's by Townsend in 1956. And you can see that these equations were thought about and derived well before we had digital computers to even solve them, 40 or 50 years later, just to start solving them. He wrote consistency in time. The stress is a balance between gain by advection by the mean flow, production by interaction between the turbulence and the mean flow, gain by convective movements of the turbulence, and by the action of pressure gradients and destruction of viscous forces. So in one statement, he basically summarized the balances and what each term in this equation from left to right means in terms of tracking the Favre average Reynolds stresses. Okay. So, by itself, this equation, 270 that is, does not lead to any knowledge of the redistribution of the Reynolds stresses and to a solution of the mean flow problem by itself. Its real value lies in the restriction on the nature of turbulent transfer process. So, by itself, it's not very useful as a closure equation, and of course you can put that in your CFD solver, but then you have all these extra unknown and very complicated terms to deal with, and not many people have used this directly in solvers. It's much more typical to take the trace of it, right, to find like an energy, and that's really what you're doing in 272. So if we set I equals to J in 270, we'll come up with 272, and this is what we call the mean kinetic energy equation, right? So this is a lot like K, again, except of course it's mass weighted, and that's the material derivative of 272 will be balanced by these right-hand side terms involving pressure, stress, and destruction type term. You'll see 272 written more in like journal articles for turbulence modeling in this form. So it's nothing but rewriting it. So let's try and look at this particular equation and what each term means. So that way we can understand how each term taken individually it's balanced physically. And I put in some red markings to try and denote that. So if we look at the first term here, and write it out in 274 and expand it, you'll have this term and this term here. So the first term in the material derivative for the trace, which is mass-weighted energy, could be the rate of change of turbulent kinetic energy of the turbulence. It's also called the advection term. The second term, which is right here, of the material derivative, that'll be the kinetic energy of the fluctuations. Or diffusion of the fluctuation energy. The next term, and this one's the first on the right-hand side, right, because it involves the pressure gradient. This will be the work due to turbulence. The next one is the work of viscous stresses due to the fluctuation motion. Oh, looks like I need my parentheses should be outside there, small mistype. What is this term? Well, it's a spatial derivative, so it's a spatial transport of turbulent energy by viscous forces. Almost there. Only two more terms in the equations. This will be the viscous dissipation by turbulent mean motion. And the last one will be the product of the turbulent stress and mean rate of strain. Okay, well, that's a lot of notes, and about that, let's talk a little bit about what that physically means. And this is where I'll make some notes. So this last term, by the way, I should say that it really links the mean flow to turbulent fluctuations through the Reynolds stress, which is what? Negative rho u I u k prime prime bar. So if we go back and look at the major equation, and we'll scroll down again, 272, right here, all the terms on the right-hand side here, except the transport terms, are going to act to destroy or produce the turbulent kinetic energy in the flow. So that's important, and that just depends on their sign. 2.72 right-hand side destroys or creates energy in the flow. Okay. All the terms of spatial gradients or time average quantities are transport terms. And they would also be sources or sinks, just like you would have in like a potential flow solver, adding sources or sinks. Okay. So only a few more notes on the general equations of motion, then we'll move on to boundary layers in a few minutes. I'd like to turn our attention to the terms that appear in the Reynolds stress transport equation in 270. And from our just observations of the terms of these equations, we would like to look at what happens when, for each term, we set I equals j. And let's look at one case, or excuse me, I not equal j. So let's look at the first term, which is the material derivative. So it's written that this is the variation of a correlation as the fluid element moves along a streamline rather than the variation of the kinetic energy of the fluctuations. So there's II versus IJ, so stress versus trace. So the first two terms, if we make this assumption of II or IJ, can be written and expanded out here on the right-hand side. There's your pressure work term, and you can expand it like this. So let's see here. Get my blue pen. This term here can be rewritten like this. And this term here can be rewritten like this. So this term here, when you see it in turbulence models for like compressible flows or hypersonic turbulent flows, this is called the general pressure diffusion term. Okay. And what's interesting about this term in the field is this will represent and force inhomogeneous turbulence into homogeneous isotropic turbulence. What's interesting about this statement is generally turbulent flows, which are highly anisotropic, have a tendency to return to an isotropic state. That's like when you have, like, say, a turbulent grid, like this in a wind tunnel, and you're flowing downstream. Obviously, your turbulent eddies and instabilities are highly skewed, and far downstream, the turbulence returns to a more isotropic homogeneous state. So these two terms in the right-hand side are forcing this turbulence to do that. And if you are able to solve the full set of equations and look at these statistics, then if they're high, then you have a higher rate of return to isotropy. That's really all the major equations formulated and how they're basically presented in the literature in the most general form for compressible flows. But we didn't do some other things. Like, for example, if you have a reacting flow, we would also have to incorporate the reaction rate equations way back in the beginning. And that's probably important for a lot of people who are maybe working in combustion. And I hear that combustion is an important thing in aerospace. And we have no electromagnetics, and we didn't really formulate these equations with body forces. So if you have strong, like, gravitational forces and stuff like that, you also have additional correlations for all those gravitational forces in a flow. So generally in aerospace, like fast atmospheric flows, we're not looking at that at all, thankfully, but they could cause instabilities in your flow too.